source at a distance. My current source lies at one point. My field is being measured at a different point. So this is one of our laws that we can use. What is the direction of A? Due to that current filament, a small increment of current. It's in the same direction as the current filament. So it's going to be in the y direction, exactly. And what about this particular current filament down there?
Negative y direction.
Exactly, it's going to give rise to negative y. So what can you say about the resultant magnetic field, the resultant magnetic vector potential on the z-axis? Anywhere on the z-axis. It's 0. Now let's use the right-hand rule and argue that the magnetic field is 0 on the z-axis as well. Based on the right-hand rule, place my thumb in the direction of current flow and my fingers curl in the direction of the magnetic field. So for this particular element, the magnetic field is going in the plus direction. If I look at this particular element, and let's assume we're staying in the plane of the blackboard for our point of observation in this particular case, our current is going downwards. My field is curling in this direction. But that doesn't subtract, does it? It actually adds to the field on the z-axis. So the field on the z-axis can't be equal to 0, can it? So now what? The key is, just like we did in electrostatics, you had a problem like this as well. The key is to take your point off the axis, because the magnetic field is related to the curl of the magnetic vector potential. The magnetic field at our point of observation is equal to the curl of the magnetic vector potential, evaluated at our point of observation. Since it's related to a curl or to a derivative of any kind of form, what do you need? You need to know the magnetic vector potential, not at a point, but at a neighborhood around a point, or at least 2 points close together. For our case, we're looking for the potential on the z-axis. That's the potential, the magnetic vector potential on the z-axis. That is a value at one point on the axis. Now we need another value at a point. Consequently, the only way you can obtain that is by allowing your point of observation to not be equal to 0, but be placed close to 0. And when you're calculating the magnetic vector potential, expressing it in terms of its integral, this will be equal to the curl of the integral around our closed loop of mu naught divided by 4 pi times our current I dl sub s. In this particular case, it's fairly straightforward. It's going to be equal to the radius of our current loop, call it d, times d phi sub s. And it's in what direction? Phi direction, which is a function of phi sub s. So let's place this over here and take our derivative out. Divided through by r, where r is related to the magnitude of r sub p minus r sub s. If I force r sub p to be equal to 0, which implies I'm either at the origin or on the z-axis, because I'm forcing z sub p to be equal to 0, I lose a piece of information associated with that curl. looking at variations along that z-axis. Consequently, allowing our point of observation to be off the z-axis, I can interchange my integration operation with respect to my curl operation. And this will be equal to mu naught times our current I divided by 4 pi times the integral. D I can pull outside as well. Can't pull a unit vector outside because it's a function of ds. But I can bring the del operator inside and its cross product. So this will give rise to the phi unit vector, a function of phi sub s, times the curl of our distance crossed into, well, I guess I'm going to have to leave phi sub s on this side in order for our cross product to be evaluated properly. And then we're going to integrate with respect to phi sub s. In this particular case, once I perform the curl, then I can take the limit where r sub p approaches 0. Now I can determine what the field is on the z-axis. See the difference. Keep in mind your properties of derivatives. You need to have it at two different positions, and then you're looking at the differences. Consequently, differential. Okay, so that's problem number 2 in a nutshell, and the difficulty with problem number 2 that I just wanted to point out. My interest is being able to use problem number 2 to extract information for problem number 3, and then use problem number 3 as a tool to start developing your design project. And using problem number 2 as a check for that design project. Now let's move on in our lectures. Last lecture we talked about the concept of the magnetic vector potential associated with the magnetic dipole moment. The magnetic vector potential at our point of observation, or our point of observation is very far from the dipole moment, was equal to mu naught times the magnetic dipole moment itself, m, where the magnetic dipole moment, m, is equal to the current is circulating an area. We'll call that area delta S. It can be called S if you like. It doesn't make a difference. We're not placing a constraint on the size of that particular current source. Cross into the relative position vector, pointing from the central location of that dipole moment to our point of observation. Last lecture, we were looking at that dipole moment in the z is equal to 0 plane. The dipole moment satisfies a right-hand rule orientation, where our fingers curl in the direction of current flow, and hence our dipole moment is perpendicular to that direction, to that plane. In our case, the dipole moment will be pointing upwards. Our relative position vector is the relative position, or the central position of our current source, and it points to our point of observation, P. Now let's make a little bit more, we stated last lecture that this particular law is a force at a distance law, and it's coordinate free. Coordinate free means we don't know what coordinate system we're in. We can pick a choice. Since it's coordinate free, we can use this law for our magnetic vector potential at any point in space as well as the origin. Consequently, let us do that and see how it all comes together. Let us choose our central position of our magnetic vector potential to be here. Let us choose our current to be flowing in this direction. Consequently, M is determined. Let us position the origin of our magnetic vector potential relative to our coordinate system, and we will identify this as being R sub S, the position of our source as generating the field. Let us position our point of observation, P, in our coordinate system and also make that general. 1, 2, let's put it